Hello. Today we are discussing or we are going to discuss electric flux. Today we will discuss what is electric flux and Gauss law. What is electric flux? Okay? What is electric flux? Today we will discuss what is actually electric flux. We will take the two examples is here. Let's say there is uniform electric field. Uniform electric field is here, and here it is 5 or 7 electric fields. Okay, 5 or 7 electric fields is here drawn, and uniform electric field basically because these all are parallel. Okay, here it is and here it is, and the plane surface is like this. The plane surface is like this, and here it is another arrangement of electric fields, the same electric fields. Okay, here how many electric field lines is here? 3 and 4 7. Okay, and here it is also we draw 7 electric fields. Here it is 7 electric fields, and the orientation of the plane is like that, is like that. Okay, so in both the two cases the electric field, in the very first case the electric field is just crossing this, and here it is also all the electric fields crossing this. You can see clearly. Okay, all the electric field crossing the surface, and in this case not all the electric fields crossing the surface. Few are left and not crossing. So basically electric flux is what? The number of electric field lines crossing any surface. The number of electric field lines crossing any surface is called electric flux. Here are all the number of field lines. Here are all the number of field lines, electric field lines is crossing the surface. The area, the magnitude of the area and the electric field lines are same. Here is also electric field is E, and here is also the magnitude of area is A. But the orientation or the arrangement you can say it is different. So that means if we increase the electric field lines, then the electric flux will increase because the electric flux is what? Number of electric field lines crossing any surface. Okay, so if we increase the number of electric field lines or electric field, which is electric field actually, then the electric flux will also increase. Okay, if we increase the magnitude of the area, the magnitude of this surface area, if we increase the size of the surface, then all the electric field lines will pass, and here it is also pass if we increase the surface area. But if one thing we are getting from this two diagrams, that means if the orientation is different, by keeping the magnitude of E and A, by keeping the magnitude of E and A same, the electric flux is different because of the different orientation of the plane. So why it is? Why it is? And we will discuss is here, and we will discuss area vector. What is area vector? What is area vector? Area vector is the perpendicular. Area vector is the direction perpendicular to the surface. Here it is area vector. Okay, here it is area vector of this surface. So the area vector of this surface is like that, of this surface is like that, and perpendicular to the surface. Okay, and what is the angle between the area vector and electric field is theta, and here it is area vector is like this, Okay, area vector is like that, perpendicular to the surface. Okay, perpendicular to the surface, but the direction of electric field is parallel to the area vector. So here it is, theta is 0, theta is 0, and here it is, theta is some 30 degree, 40 degree, something else. Okay, so the angle between the two, between these two, E and A, area vector and electric field, is different, and all the things is same. So in both the cases the electric flux is different because the number of electric field lines passing this and passing this is different and different. Okay, so electric field is also different. So basically, by all the discussion, the basically electric field is electric flux is represented by phi E. So phi E basically proportional to E. If we increase the electric field lines or electric field strength, then the electric flux will increase, and proportional to A. If we increase the area, the number of electric field lines will cross more, and also proportional to the cos theta. Cos theta. And why it is cos theta, not sin theta? Why it is cos theta? Because 0 degree, for 0 degree cos theta is 1, and here is the some flux. If we take sin theta, then sin 0 will become 0, and the value of flux will make it 0 by the sin 0, and here it is some flux, so we cannot take sin theta. Okay, we just take cos theta, because the 0 degree cos 0 gives the value 1, that is the maximum, and here we saw here there is some flux and the maximum flux. Okay, so just we take here phi E is nothing but EA cos theta, EA cos theta. Okay, for total flux. Okay, for total flux. ठीक है, total flux. But for very small area, for very small area means infinitesimally small, phi E d phi equal to EDA cos theta. Okay, for very small area like that. Okay, this one is dA and here it is E, so we will get the electric flux like this. This one is dA. dA is very small area or areal element, and in vector form we can convert it. D phi E is equal to E vector dot D vector, and the dot product of these two quantities will get like this. Okay, so here it is, electric flux basically E dot A. Now come to Gauss law. Gauss law. Okay, what is Gauss law? Gauss law basically stated that total electric flux through any closed surface, okay, come out through any closed surface is 1 by epsilon naught times to the net charge. And net charge, how you will get net charge? Net charge is the algebraic sum of all the charges kept inside the enclosed surface. So whether it can be negative charge, positive charge, first we will take algebraic sum of all the charges, then we will get the electric flux through the enclosed surface, but only inside charge. Okay, only inside. We will discuss later uh, if the charge is just outside the surface, we will discuss later. Okay, so we are going to prove it. Okay, we are going to prove it first. If we will prove it, then we have to take Gaussian surface. Let's say here it is the point charge. Okay, and at this distance we take the Gaussian surface. And at this distance we take the Gaussian surface. and closed, it is closed, okay. And here it is very small area, here it is very small area dA, and the vector of it dA vector, which is perpendicular to the surface, and already discussed about it. And due to this charge at this point, at this area, the electric field is like that. And here is the radius of this Gaussian surface. The point, let's say point P, which is at the distance r from the charge. So we start for very small area. Here we have take dA for very small area. So d phi E is the electric flux for very small area. For very small area, okay, and of the dot product. If we want to calculate total electric flux throughout this Gaussian surface, then we have to integrate it, and the integration of d phi E is phi A. And here it is, the electric field is constant at all the points on the Gaussian surface, at all the, which is because all the points on the Gaussian surface is at the equidistance from the center or from the Q, that is R, okay. So we take, first we have to take the dot product, sorry, first we have to take dot product. And what is the dot product? EDA cos theta. And what is theta is here? The angle between the area vector and the electric field, that is 0 degree. So cos 0 is 1. So just remain here dA and E. And E we take outside. And what is the integration of this? And this is the sphere, actually Gaussian surface. Gaussian surface. Okay? Gaussian surface. Gaussian surface. And that is a sphere. And what is the area of a sphere is just 4 pi r square. So just we put here 4 pi r square, because the integration means the total value of anything. If we integrate something, then we take the total value. And what is the electric field due to this Q at this point, at the distance r? What is the electric field? E is 1 by 4 pi epsilon naught Q upon r square. And here it is A 4 pi r square. So phi E is just Q divided by epsilon naught, and which is nothing but a Gauss law, which is nothing but a Gauss law. So here it is, we have cleared the electric flux come out through any enclosed surface, total net charge, and 1 by epsilon naught. Okay, so we can state it like that: the total electric flux throughout any enclosed surface is equal to 1 by epsilon naught times 1 by epsilon naught times to the net charge enclosed by it, enclosed by it. And here it is some, don't be confused like that, here it is closed integral, because the surface is closed, so that we take closed integral. You can take it like that, closed integral, okay, closed integral. Now we have to solve one question like that. One thing is remaining: Gauss law or closed surface through any, sorry, the electric flux through any closed surface, the electric flux through any closed surface is independent of the shape of the surface. Even it can be cube, okay, the electric flux will be same, the electric flux will be same, okay. Even it can be sphere, the electric flux will be same, okay, the electric flux will be same. Even it can be cylinder, and here it is also electric flux will be same. That doesn't matter which type of enclosed surface you are considering, okay. So let's say one question is here. Let's say here is the state conductor and the charge is uniformly distributed on it. Okay, uniformly distributed on it. And here it is linear charge density lambda. And the side of this, sorry, first we have to make this cube properly. Okay, here it is. Here it is the edge of the cube A. So how much electric flux will come out from this closed surface? You can see this only portion of the state conductor or state charge inside the closed surface. So we just take this and here, what will be of length? This A length, because here it is the same value we will get it here. This only pair. So from this to this. So from this to this is A. Okay. This only the only charge on this length will inside the cube. So what is flux here? Phi A is nothing but Q divided by epsilon naught. And what is lambda? Lambda is nothing but Q by L. That is Q by A. So what you will get it here? A lambda equal to Q. So here it is A lambda upon epsilon naught. So the question I think just mains or advanced questions. Okay, we have done it here. So the electric flux is just A lambda divided by epsilon naught. So the final conclusion from the Gauss law is just it is valid only for closed surface. Okay, whether it can any surface, but it should be a closed surface. Okay, the same electric flux will come out through any surface. Okay, and which is equal to Q divided by epsilon naught. I hope it clear to the all the students. Thank you.